Good morning, and today we are talking about number 3. So number 3 was state and prove the fundamental homomorphism theorem, which is a theorem about homomorphisms and isomorphisms, really. So it goes something like this. There's a lot of different ways to say it, but this here anyway is sort of the most concise version of it. This part. So let theta from G to H be an onto homomorphism, meaning all of H gets covered by theta of G, and then let K be the kernel. Then it turns out G mod the kernel is isomorphic to H. So in other words, whenever you have any homomorphism that maps all the way onto here, whatever you get over here is the exact same structure as if you took what was originally in G and modded out by the kernel. So it tells you that whenever you have a homomorphism from G to somewhere else, the structure there, can only be a quotient group of G. It's got to be, because that's the only way, that's what this theorem is saying, is that the only homomorphic images of G are the exact same, isomorphically anyway, as the quotient groups of G, all the possible quotient groups of G. So yeah, that's one interpretation of the theorem. Anyway, the slightly longer version is the next part, which gives the details of the isomorphism. It says, this map phi, which takes in a coset and spits out an element of H, is indeed the isomorphism between G mod K and H. So sometimes people also like to write it with this little diagram. They say, suppose you have this situation, you have a group G and a theta onto H. And then, of course, you've also got this, right? They call it the natural homomorphism or the projection homomorphism, the one that just takes the elements in G and maps them to whatever coset they're in the quotient group. Well, the theorem says that if you have this situation, then these two are guaranteed to be isomorphic. Now, I draw the double arrow to really hammer home that it's equivalence, but technically the isomorphism is a function that only goes in one direction. In particular, it only goes in that direction, but it also has an inverse function which goes the other way just as well. So, yeah. Okay, so how do you prove this theorem? So I have a student submission for this one. They had a very thorough response here. And here's how it goes. So first of all, state the fundamental homomorphism theorem. Give 5 points for that if you stated it correctly. And then the second part is prove. So they go right on ahead and define this mapping phi. And it's going to do exactly what it says there. It's going to take a coset in here, and it's going to turn it to an element in H. And how is it going to do that? Well, it's going to, what's the word? I can't think of the word. Ask theta. It's going to ask theta. It's just going to be like, hey, theta, where this coset I have, GK, that element G, where would you send that to? Okay, that's where I'm going to send GK to. Right, so that's kind of what phi is doing. And so you could express that like that phi of AK is equal to theta of A. And again, this is an element in the quotient of G, whereas this is an element of H. So, yeah. Okay, so we got to do a couple things. We got to show that this phi is an isomorphism. So first of all, you got to show that it's a bijective homomorphism. So we'll get to that. But before that, though, you got to show that it is well defined, right? So just to be clear on what that means, because I found it super confusing when I was in this class, well defined is something that you got to ensure for functions which act on things that have multiple names. So you know how one coset can have multiple names, then you'd better make sure that they go to the same place, right? So for example, if you're talking about, let's say the rational numbers have multiple names. You'd better hope, if you got some function defined on the rational numbers, if you want that function to be well defined, you'd better hope that if you give that function 3/6 and then you also give it 5/10, that it does the same thing to both of those numbers, right? If it treats those numbers differently, then it does not treat them the same, and so it's not acting like the rational numbers that are supposed to be equivalent to each other really are equivalent to each other. So in other words, this function that I'm making up is completely bullshit. It's not well defined. And that's what we got to make sure for this one, that is this bullshit. If I give it a coset once by calling it AK, but then later I give it the same coset, the exact same element of the quotient group, but I call it different. I call it BK. Well, then that's going to map to theta of A and theta of B. And are those the same? Because if they're not, then this function is not well defined, and we got to stop right there. So let's make sure that that's the case. So this person did it like this. They looks like they multiply both sides by B inverse, and so it becomes this, and that's one definition of what it means for something to be in there. And then what does it mean to be in K? Well, K was the third. Let me try again. K was the kernel of theta, which means when you plug it into theta, you get the identity. And that means, if you expand that out a little more, that means that theta of B equals theta of A. And that's exactly what we were hoping for. So it turns out that when you have this thing that takes in these cosets, it doesn't matter which of the elements in that coset you use to name it. No matter which name you use, it'll always work out the same. So yeah, so it turns out that this function phi is indeed well defined. Okay. Now for the other part, right? Is it a homomorphism? Yes. Well, they're just trying to take that and show that that's the same as that. And sure enough, it is, because you multiply the cosets together like that, and then that's the meaning of that, and that's a homomorphism. So then you go back the other way, and then boom. So yeah, so it ultimately depends on theta being a homomorphism, which should make sense because it was defined pretty much as just whatever you were plugging into me, plug it into theta instead, basically, right? But drop the K, but whatever. So yeah, so the point is it respects the operation, it is a homomorphism, and then finally show that it's surjective. So remember, this student actually forgot. Whoops. This student actually forgot that theta needs to be onto H, right? And that should make sense, because if you have G and G is getting mapped onto H, then everything in H kind of came from G. And so the structure of H should have something to do with the structure of G, and that's what the theorem is elaborating on. But let's say that instead, what if G maps into H, but there's like a whole lot more to H than what G gets set to, right? Well, then who knows what the hell is going on there. I can tell you what the structure on just that portion, just that subgroup that got mapped onto, I can tell you, oh, that's isomorphic to G mod K. But the rest of it, I don't know. So you can only have this super nice version if it's an onto homomorphism, is the point. Or you can say it can be whatever type of homomorphism you want, but then you just restrict your attention to theta of G as a subgroup of all of H, because it's onto that, of course. But yeah, anyway. So, in my opinion, best way of defining everything is just make the theorem only work for onto homomorphisms. So, that's why it's legit for this student. I didn't mean to do that. That's why it's legit for this student to be like this. Because any element of H, you can't always do that. But if theta is onto, then any element of H can be described as theta of something. So that works great. So yeah, so they can just call it like that. And then similarly, that means it can be described as phi of something as well, right? Because phi and theta are almost the same. So, yeah. And then finally, show that it's injective. So if two cosets have the same image, well, then the two cosets must have actually been the same. So let's see. If they have the same image, if these are equal, well, then you run the same trick as before, and it means that theta of B inverse A is the identity, which means B inverse A is in the kernel, which means B inverse AK is equal to K, which means AK is equal to BK. So if you have two cosets that have the same image under phi, then they must actually be the same coset. So that's what it means for it to be injective. So this person just verified that it's well-defined, that it's homomorphism, and that it's a bijection. Well then, boom, phi is an isomorphism. So there you go. So it turns out that quotient group mod the kernel is always isomorphic to the image of whatever you were doing, right? So if ever you got any kind of homomorphism like this, well then just think that that structure that you're going to is actually the same structure as G, something that was already in G. So it's like the structure that you're getting was already in there. It's inside of G. You just have to mod out by that K, by whatever your K is for that situation, and then it's going to be the same as that. So it's got a great name. It's called the fundamental homomorphism theorem. Sometimes I've also heard this, and that's a pretty good name too. But both of those names, I hope, emphasize the importance of this theorem. So definitely keep this one at the top of your toolbox. Okay, that is it for number 3, and I will see you on the next one.